Okay. Good afternoon. Please. Quiet, please. We shall start in a few seconds. So now it's a presentation of solutions. So I hope that you enjoyed problems we prepared for you. We saw many nice solutions. So it was really enjoying. So please find a place to sit so we can start as soon as possible. We are a little bit late, but we prepared for a presentation of solutions for you, and now it's time to present it. So I would like to invite our judges to podium. So let's start. So the first problem will present Roman.
Okay, thanks. So the first problem was silence of the lamps. It was the easiest problem, which many of you found out. It's basically just about using 3 for loops to pre-compute the number of possible volumes, then doing a prefix sum, and of course there's the key observation that you can pre-compute all the results at once and not do it for every query. And since there are only like 200 million of those for loops are sufficient. So who's next?
Já nevím, jak to funguje, ale.
Prostě mačkáš tohle, když chceš další slide.
Okay. Hi, Clockwork Orange. It was basically about having an integer and having an operation to shift it and or it to the previous integer, like the previous state. And it was only 40 characters long, so as you could have seen, it took at most 6 operations to do so. So, in fact, you could have brute forced it or run some BFS or BFS, I don't know. So well, that's it. Just like that. Okay.
Okay, matrix was also one of the easier problems in the set. And you just counted the trinities, that was all. The only little trick that you had to follow was that it was impossible to count from every place starting up. So, for example, when going from the top left corner down, so if there is some larger trinity, it always has to be a combination of the 2 trinities here. So basically you just go over the matrix, and when you find these 3 characters are the same, you just look at the result for this field, and you can see immediately how many trinities are there. So that's about it. The estimated or our expected time complexity was n squared and it was one side. It should be it. One more problem, trigam. It was about mapping nodes of a tree to some existing points in the plane, such that the edges should not intersect. As trees are recursive structures, so the solution is also recursive. We start with the root node, and with some point, let's say it's the leftmost one, and we map this point to this vertex, and then we see we have 3 subtrees with 3 vertices, 2 and 2, and we can sort all of the points by their angles, and the first 3 become mapped to the first subtree, the second 2 to the second subtree, and so on. And then we proceed to this node, choose this one, and then we sort vertices in this order and repeat the procedure recursively. So the expected time complexity is n squared times log n, because n log n is one sort, and we do the sort for all of the points.
The next task was stones. So that was a game of 2 players where we have piles of stones, and one player can take one amount and the second can take second. So Obviously, if both players can take the same amount, we have basically a NIM game, which can be solved by XORing the piles, the numbers of piles. However, the interesting case is where we have different numbers for those players. So assume the first player has a bigger one. And in this case, he can possibly make a zero move, which will win him the game if he then ties his hand and plays the normal NIM game. So we look for the piles of size bigger than b+1. And if there is one, the player A can play a zero move and win. Otherwise, if the B is playing first, he can avoid this case. If there is only one pile which is big enough, if he can play in that pile and make it small enough to continue with the classical NIM play. If there are two piles which are big enough, then he has no chance of winning. So the solution is to compute the size of piles, look for the big piles, and look if the NIM can be one.
So next problem is ABCD murder. There are quite a few solutions to solve this problem. Some with linear complexity, some are a bit slower, but we accept it even n times square root of n. So the basic idea is, if we imagine that we got someone to tell us which part of strings, which part of the input string can be matched to some words from the dictionary, then we can solve it greedily. So once we figure out this part, we can greedily iterate. Kinda we know that we gotta match the beginning of the string. So if well, let's show you an example. So this was one of the samples. In the first step, you matched no character. So basically you gotta match the first A plus possibly something more. So you can find out that you can match the words AB and ABEC. The longest one is what we need. So we take that. Then we got matched the first 4 characters. Then again, we need to match the 5th character. So basically, we need a word that starts at first 4 indices or possibly at the 5th one. And again, we want to match as much of the string as we can. So then we can match the word CEDA. And that's the whole idea, kind of 2-pointer technique. And now how to find these matches, these kind of overlapping intervals. So one way to solve this problem was use Coracic. We basically built an automaton using all the strings from the dictionary. And then there's the key observation that we don't care about all the matches. All we care about is that we can match some string that ends at a given index, and that we need just the longest string. So basically what we need is to find out the longest string that can match at the given index. And this part can be pre-computed in linear time. So when we process the string, we kind of keep asking, oh, what longest string can I match here? And then use this information and apply it in the greedy part. So the overall complexity is linear. You could also use suffix array or some other alternate solutions. We won't go through these here, but you will have these slides on our website so you can see for yourself.
So, Shooter Island, we have an area
or a grid with 50 rows, but 100,000 columns, and we are hitting some rectangles, and we want to keep track of connected components on the unit squares. So we use disjoint set union structure. But the problem is if we keep hitting big rectangles, then we would be going through all the points all the time. But we want to avoid this. So when we are hitting a rectangle, we want to quickly extract the list of unit squares that are newly hit. And to do this, we use the fact that we have just 50 rows. So on each row, we build again a data structure, a disjoint set union data structure that will tell us for each square where the current component ends. And then when we are hitting a rectangle, we hit each row separately. And then when we edit, we just go through the not yet hit points. So the amortized complexity is just the total size of this grid.
Thanks. So this problem was about you holding your dog on a leash, throwing him a frisbee, and then waiting for him till he retrieves that and brings it back to you. So it's kind of math. You got the vertical acceleration for the dog and the frisbee. Basically, you could solve it in several ways. These are just some of the formulas that you might use. There are more ways to figure it out. Probably the easiest solution is to use binary search and find out at which time the dog can catch the frisbee, and of course then bring it back. So the first observation is that the dog always jumps with maximal velocity. Since it can move freely while it's airborne, it doesn't really matter. So if he can move horizontally as he wishes, even in the air, he can always jump at maximal velocity. So then we kind of compute, when we guess the time, we know exactly where the frisbee is going to be. If we know that there's a time t, we can figure out, oh, the frisbee is flying for time t minus tf, etc., and compute its x and y coordinates, and then simply figure out whether the dog is able to achieve those. We can solve it for x and y coordinates separately, and figure out if it's able to handle the x coordinate, if it's able to run fast enough to get there in time, and also if it's able to jump so high in sufficient time. There's just the catch that some teams forget to test where the frisbee isn't high enough. And also you could solve it in a way that you kind of case the whole thing into three main cases. Either the frisbee will hit the ground and kind of wait for the dog to fetch it, or the dog has to wait for a bit because the frisbee is too high, or the dog can jump for a frisbee immediately and maybe still in the air come back to its owner.
So in the problem of the incredible hull, we first have to get through the problem statement and observe following procedure. At first, we consider points that form the convex hull. Then the hull will be divided into triangles, where all edges go from one point to all another. And after that, all non-empty triangles are recursively split into 3 triangles. So let's say it goes like this. This one, this one, this one, and in the end, this one. And that's the end of the procedure. So what can we observe from this? If there are any points inside the convex hull, they form cliques of size 4, which is always the point and the points of the triangle that it was split in. And it also works in the recursive case, like there. So we immediately have that the number of such cliques is the number of points that are inside the convex hull, unless, of course, there are none of them. In that case, we have only cliques of size 3. And the only non-trivial part is to compute how many points on the convex hull also are included in these cliques. And this can be done by sorting the points by their angle and linearly going through them and finding empty triangles. So, and it turns out that we don't have to simulate the process, but only find the convex hull and do some linear scan. So the target complexity is n log n for convex hull and for sorting.
Okay, so the bridge, then in this problem you had some danger levels. So first step is to divide the problem by danger levels, since there were only 10 danger levels. So it's 10 times the complexity of the solutions. And after the dividing, you had some dynamic connectivity. And there are several ways to do so. I think best way was to do it offline and divide the queries into blocks of size square n, and in each of the blocks, for each edge, you computed the time when it started to exist and the time when it ceased to exist. And then for each block, you computed some some union find, and then you could easily, by some DFS, find whether the points are connected. Well, it was one solution. Another solution, I guess better one, but maybe it requested more work, and it was to, well, actually do the same at the beginning and then divide the edges to halves. And I don't know, you can also use union find, but it wasn't necessary for this solution. And you just divide the queries to halves and make some graph from the edges, for which you know they will surely be in the second part of the division. And you can also observe that in every division in a time division there is very limited number of nodes which are used there, which we either ask for or for which we add the edges or for which we delete the edges. So by this divide and conquer technique, we should be able to compute it in logarithmic time. And well, it was also possible to do so online, but it's very hard. So I think I can pass this already.
Okay, so in the problem of Lord of the Kings, we first start with creating a graph which represents the particular movement pattern, and then finding the minimum number of tiles to connect all interesting vertices is basically equivalent to finding a Steiner tree which connects these interesting vertices, which are cities and the palace. And we can, thanks to the size of the problem, we can solve this by some dynamic programming. And the idea is to compute all possible Steiner trees for all routes and all subsets of terminals. We can afford that. And how do we construct such trees? We can do that by in two ways. Either we can connect two subtrees rooted at the same vertex, whose subsets of terminals form exactly partition of the desired subset. So the new resulting tree will be rooted at the same vertex and connect all the terminals. That's one way. And the second one, we can take already tree rooted at some vertex and push its root to some other vertex. So effectively creating a new root of the tree. So the only problem is that extending or this extension costs the length of the shortest path between former or the previous and new root. So we also have to pre-compute all pairs shortest path in the graph. But thanks to the size of it, we can even afford to use Floyd-Warshaw's algorithm. So that's not an issue. So basically, how do we fill the dynamic programming tables for each subset of terminals, for each root, and for each subset of this subset that determines the partition? We try the join operation, and similarly with the extension. So for each subset, each old root, and each new root, we try to construct a new Steiner tree. So the resulting time complexity is n times 3 to the t. That's for the join operation, plus n squared times 2 to the power of t. This is for the extension operation, and this one n cubed for the Floyd-Warshaw's algorithm.
And the last task was minority report, where we have lines and start and the end, and the particle which starts from the start can be reflected by the mirrors, but they can reflect the particle only once. So then we can pass the mirror through. So the basic observation is that thanks to the disappearing mirrors, each subset and each permutation can be used only once to generate a unique solution, possibly. And so we just try every subset and every permutation of this subset. Also, we have to detect if the particle would be too close to the corner, thanks to the guarantee that there are no close reflections from the corner. We can just see if it's too close and then just ignore it in that case. So the basic idea is to use reflections. So we decide which mirror will be used first, and then we reflect the whole plane by that mirror. And then we see that we get to the second mirror, so we also again reflect the whole plane. Now we have a just line segment, and we see if we can get through the mirrors that we decided to get through. It's possible that some other mirror will be in way. In that case, it's not possible. Also, we have to take care of the special cases where we can pass through a corner which is no longer there. It's also possible that this happens. So, just few cases for amusement now. So this is the typical case, this is more typical case, and this is the worst case that we found out.
Okay, this was the last problem. Thank you very much for such nice presentation of the problem solutions. Thank you. And okay, thank you for your attention. Do you have any questions related to problems? To problem set?
So this is actually a photo of our system guide at 1 p.m. today.
Okay, so if there are no questions related to problem set, then the schedule as it was announced. So the next event is the Abort Announcement, which will be held in Bethlehem Chapel. So there it will start at 6 p.m. So thank you so much. Now you have some free time to put your bags to the hotel and then go to that place. Okay, thank you so much.